Here I'll have an example of this RSA crypto system in action. Well, we will do our computations by hand, so let's choose some reasonably small numbers, some 2 prime numbers, 11 and 17, and the beginning of the algorithm is well, it's not the complete data for encryption and decryption. We should choose our encryption and decryption keys, and they have to be numbers which are invertible modulo the earliest function of PQ, which in our case is 11 minus 1 times 17 minus 1, 10 times 16, 160. So that is the sort of universal cycling behavior modulus for the powers of invertible things, but we need to find something which is co-prime to this 160, so that means co-prime to 2 and 5, and the easiest such will be 3. So we have to invert now, find the inverse, multiplicative inverse, modulo 160 for that number. So that can be done by perhaps simplifying the problem, looking at shadows of these congruence modular factors of the 160. Co-prime factors, they will be 32 and 5. So I need to invert 3 modulo 32 separately and modulo 32, and then combine them into the unique remainder modulo 160. That will be my decryption key. So what do I know? 3D is congruent to 1 modulo 5, and 3D is congruent to 1 modulo 32. Simultaneously, that is equivalent to the required congruence. The inverting 3 modulo 5 is easy, so D has to be 2. Inverting D modulo 32 is also easy. Well, if I just plug 11, I'll have 33, which is 1 plus 32. So yes, these two separate congruences are, modulo 32, are easy to solve. This passage back from 2 shadows to the complete story, this Diophantine equation really is what is left. So I can write my D in the following templates. I can write it as x times 32 plus y times 5, and then using these congruences find x and y, well, modular corresponding moduli. So if I look at, if I plug this template into the first congruence, I'll have this term disappearing, and then x times 32 will be congruent to 2 modulo 5. So that 32 can be replaced by 2 modulo 5, and so I have x being just 1, having a remainder 1 modulo 5. So the same for modulus 32. If I look at this and replace D in this congruence, then I will have some condition on y, namely 5y will be congruent to 11 modulo 32. So now I have to invert 5, put it on the other side. Well, so what can I do? What is the inverse of 5 modulo 32? If I double 32, I will have 64. So 64 is one step away from 65, which is a multiple of 5. And what is this multiple? So that will be 13 copies of 5. That is literally 65, and that is 1 plus 64. So that is congruent to 1 modular 32. So I have my inverse, it's 13, and now I can multiply this equation and find my y, and after that I'll be able to find my d. So y is the product of 5 inverse and 11, so that will be 13 times 11 modulo 32. Just to simplify it, I will just multiplying, I will have 130 plus 1343 modulo 32. So what can I do? I can say take 6 copies of 32. That will be, no, 6 is too many. Take 4 copies of 32, so it will be 128. Take it out, that will not change the congruence class. I will have 43 without 28, 23 without 8, 20 without 5. I'll have 15 left, modulo 32. So that is what y is, or its remainder modulo 32 is. X is being 1, so then I just have to combine them to find my d finally. So I'll have 1 copy of 32 and then 15 copies of 5. So that is going to be what? So that 15 copies of 5 or 5 copies of 15 better is going to be 75. And so I have 107 modular the composite module 160. So that is my decryption key. That is going to be my decryption key. So now I have to choose a message, choose a number modular the product of my primes 11 and 17. So that is 170 plus 1787. And whatever I have to send, I have to encrypt. So yeah, let me choose it to be, say, 10. And then the encryption will consist of raising it to my encryption key power. So that will be cubing. Well, with my choice, it's an easy process. I just have 1000. But that is not what I send. I have to reduce, everything has to be brought down to the remainders modulo, my operational modulus 187. So that has to be replaced by its remainder modulo 187. So what I can do, I can subtract 1870, it's a multiple of 187. That will flip me into the negative 870, and then I could just bring back to positive by looking at some multiple of 187, so maybe 5 copies. So that will be 500 and then, yeah, 935. So 935 without 870 is 65. So that is modular 187. And that is the U, that is the message which is sent. It's just 65, and the modulus is, of course, of public knowledge. So now if the other party are now receiving this encrypted message, I have to decrypt it, and the decryption will consist of raising whatever I receive to the power 107. So that's what I need to find. And then reduce, of course, to its remainder modular 187. And that has to give me back has to give me back the send message. Has to give me the send message. So that is the computations I'll be doing now. I will do it using Chinese remainder. I will use modulus 11 separately and modulus 17 to compute that power, the remainders of that power, and then I will combine them into the answer, into the unique answer. So first 65 to the power 107 modular 11. Well, modular 11, 65 is as good as -1 because it is one step to the left from 66, which is 0. So that's what I write. 107 is an odd power, so I still have -1. And well, I can flip it to the positive range back. It is 10, modular 11. So 65 to the power 107 modular 17 now. First, the base, simplifying the base. So I have to bring it down to something smaller, modular 17. What can I do? If I take 17, 4 times, I will have 40, and then I'll have 7 times 4, which is 20. I'll have 68. So that will be 65 without 68. That will be -3 modular 17. So that allows me to replace my base by -3. So that's just simple modular arithmetic. The next step has to deal with the power, so that will be using Fermat's theorem, because we are working modular a prime 17. So 107 can be reduced by copies of 16, because that is the cycling behavior. Obviously 65 is non-zero modular 17, so we can apply this version of Fermat's theorem and be sure that 16th power of 65 is congruent to 1 modular 17. So we can take them out of our exponent. So how many? Yes, we can perhaps take 16. We could take just, okay, I'll start with easy reduction by taking 10 copies of 16, so that will bring me to the into the negative range. I'll have 60 without 7, I'll have 53 with minus sign. And then what can I do to bring it back to positive? Perhaps I can add 4 copies of 16, which will make it 64. So this will bring me to the positive range. That will become 11, which is the same if I like to if I like to have it smaller in absolute value, I can just take another copy of 16 out, so I'll have -5. That is all true modulo 16, and 16 is this modulus, reduction modulus for the power. So what I can do, well, maybe I will do that. I will just flip to the negative power. So I'll write it as a -3 to the power -5. Well, that I can simplify, write it differently as negative, minus sign comes out, as negative power of inverse of 3, multiplicative inverse, and the power will be fifth. So I need to know multiplicative inverse. That's a simplification. I didn't want to compute the 11th power of -3. I could find in the inverse, I could compute the fifth power of the inverse. That will be the same. So what is the inverse of 3 multiplicative inverse of 3 modulo 17? That is all modulo 17. Multiplicative inverse of 3 modulo 17. If we just increment 17 by 1, we'll get 18, which is a multiple of 3, and that is 6 multiple of 3, so that is our multiplicative inverse. So that is as good as raising 6 to the fifth power and then taking a negative. So what is the fifth power of 6? Let's compute the square. So 6 squared on the nose is 36, and 17 fits twice inside, so we can subtract 34, which is twice 17, and we will be left with 2. So then the fifth power I can replace by the square, and a copy of 6. So that will, after getting rid of squares, replacing the squares of 6 by 2, I'll have 2 of them, and then I'll have a copy of 6. So that is 4, that is 6, I have -24. -24 I can shift by 34, and that will bring me to 10. And now I have both powers giving me the same remainder 10, so by the Chinese remainder theorem, my W, which is the power of 65 to 107, has to be of remainder 10 modulo 187. So successfully recovered the send message. The algorithm worked for me. See you later.